Good day, everyone. This is a review of Wetzel's Limnology textbook, the fourth edition. This is chapter 3, Water as a Substance. And it is written by Rich Pavlovitz and Ram Yerubandi. The characteristics of water. Water dominates the composition of liquids on Earth, including its lakes and oceans, as well as the compositions of all living organisms. It is therefore an important fact that the physical and chemical properties of water are rather different from those of many liquids of similar molecular structure, with, for example, significantly higher melting and boiling points, surface tension, and viscosity. In addition, the properties of water in the liquid state often change in complex ways with temperature and pressure to a degree not seen in other liquids. Many of these subtle variations are crucial to regulating the physical, chemical, and biological processes that govern natural waters. In turn, aquatic biota have developed many adaptations that take advantage of these features to improve sustained productivity. For practical purposes, when studying lakes, it is therefore important to understand and quantify the properties of water. Macroscopic physical properties of a liquid can be classified into several categories. Thermodynamic properties like heat capacity, density, and the speed of pressure waves, for example sound, describe the state of the liquid related to the type and arrangement of molecules within it. Transport properties like viscosity, as well as thermal and electrical conductivity, describe the rate at which quantities like momentum, heat, and charge are transferred. Finally, interface properties like surface tension and refractive index govern changes that are associated with the boundaries between different fluids. Although water in nature is never found in a pure state, the mass fraction of other dissolved matters in fresh waters is usually small enough that its presence with individual molecules separated by tens of water molecules causes only small changes in most properties relative to those of the pure substance. The properties of pure water can therefore be a useful first approximation to the properties of natural waters in many, although not all, cases. Exceptions include electrical conductivity, which is mostly controlled by the small number of dissolved ions present in all natural waters, and the properties of brines, including seawater, and hypersaline lakes, where as few as 2 to 4 water molecules can separate those of the dissolved salts. Molecular structure. Many of the anomalous properties of water can be explained by its unique chemical structure. Pure water is made up of hydrogen and oxygen atoms, which combine to form the water molecule H2O. In equilibrium, the nuclei of the H2O water molecule form an isosceles triangle with a slightly obtuse bond angle of just under 105 degrees, separating the hydrogen atoms at the oxygen nucleus. As a result of this angled shape, charge distribution around the molecule are not symmetric, even though the total charge is balanced. There is an apparent negative charge located near the central oxygen atoms and positive charges near the hydrogen atoms. Thus, the molecule has an electrical dipole moment. The polar nature of the water molecule allows for a special type of bonding called hydrogen bonding between water molecules and between water molecules and those of other dissolved substances. Hydrogen bonding is mostly electrostatic, but due to the sharing of unpaired electrons, it is also partly covalent in nature. Even in a liquid, this leads to the formation of lattices, clathrates, cages, and polymers. Water is then a highly structured substance, although these structures form and reform on very short time scales. In ice, the time scales are around 10 to the minus 5 seconds, and in liquid water, about 10 to the minus 11 seconds. There are many consequences of this tendency toward a structured form. In pure water, these structures are difficult to disrupt, leading to anomalously high melting and boiling points, as well as large heat capacity compared to other liquids. However, these structures are also much less space efficient than would otherwise be possible, so water contains voids. The normally occurring form of water ice on Earth's surface contains a tetrahedral structure with many voids, so its density is significantly less than that of liquid water. As water melts and warms, molecules reorient and rearrange themselves into a denser packing with fewer voids, helped by a slight bending of the hydrogen bonds. Liquid water then sinks below lake ice during surface cooling, and this ice in turn insulates the water below from further heat loss. However, the greater thermal agitation that arises from warming also causes molecular distances to rise, acting to decrease density. In liquid water, the changing balance between the tendency toward closer packing by reorientation and the tendency toward greater spacing by thermal agitation as temperature increases results in the density reaching a maximum at 3.98 degrees centigrade instead of the freezing point. When dissolved matter is present in the water, the tendency of water molecules to form structures around ions are called hydration. Itself has many ramifications. Hydration greatly increases the solubility of many substances in water relative to their solubility in other liquids by acting to separate them into positive and negative ions. It leads to unexpectedly low hydraulic electrical conductivities associated with some ions, as applied electrical fields must accelerate not only the ions but also water molecules attached to them. The formation of polymers also complicates the reactive behaviors of elements like silica in water. Although the most abundant forms of hydrogen and oxygen that make up water are H1 and O16 elements in the natural world are found in a variety of isotopes. H2, or deuterium, is a stable isotope of hydrogen, typically making up between 60 and 180 of every million hydrogen atoms in nature. However, the unstable H3, or tritium, isotope with a half-life of 12.5 years was noticeably present only during the era of atmospheric nuclear bomb testing. Stable isotopes of oxygen found in nature are O17 and O18 in amounts ranging from 370 to 400 and 1880 to 2200 ppm respectively. A reference state for the isotopic concentration of so-called ordinary water is Vienna standard mean ocean water, produced via the distillation of seawater, in which H2 makes up 156 ppm of hydrogen atoms, and O17 and O18 respectively make up 379 and 2000 ppm of oxygen atoms. Although isotopes do not behave differently in chemical reactions, their different masses causes small changes in physical properties. For example, density and freezing points are higher for water containing the heavier isotopes of hydrogen. More importantly, isotopically different water molecules evaporate and condense at different rates, and these differences depend on temperature. Thus, their ratio in a water sample from one stage of the hydrologic cycle can be different from their ratios in a water sample from another stage, and these differences may vary with temperature. If water molecules are then incorporated into solid compounds or into organisms formed within a lake, which then die and are preserved over geological time, measurements of isotopic ratios within them can be used to estimate temperature conditions at the time of their formation. Thermodynamic properties. Properties of waters have traditionally been determined through purely empirical measurements at different temperatures and pressures, to which analytic functions are fitted. Property values can then be calculated at any temperature or pressure using those functions, even if no measurements have ever been made at exactly those conditions. These so-called correlation equations are often determined independently for different properties. However, different thermodynamic properties are linked through theoretical relationships, and so inconsistencies can arise in their estimated numerical values. Depending on how the property was calculated in recent years, it has been recognized that a better approach is to define thermodynamic state function for liquids like pure water or seawater. These state functions are not directly measurable, but all thermodynamic properties can be uniquely derived from specific mathematical derivatives and or sets of derivatives of these state functions codifying the thermodynamic interrelationships. Thus, it is possible by integration and fitting to consistently summarize measurements of all thermodynamic properties of a particular liquid in a single thermodynamic state function. The availability of a state function also allows useful but otherwise unmeasurable thermodynamic properties like enthalpy and entropy to be quantified for this liquid, as they too can be derived from the state function. A thermodynamic state function for pure water is specified by this standard, IAPWS-95. In some situations, the effects of salinity are important, and an extension of this standard, which includes salinity called TEOS-10, may be useful as a description of saline surface water, even though it officially describes seawater. The mathematical functions defining the state function are quite complex, and it is recommended that existing software carefully written to compute thermodynamic properties according to this standard is used. However, the composition of dissolved matter in continental surface water is rather different from that found in seawater, and the accuracy of the resulting property estimates using seawater equation with a non-zero salinity except for density and electrical conductivity has not been evaluated for this saline surface water. Density, water and ice. The density of water is probably its most important property for understanding the physical dynamics of natural waters, although the IAPWS-95 standard specifies the recommended mathematical function for numerically computing any of the thermodynamic properties of water at any temperature or pressure for pure liquid water density ρ in the restricted range of temperature T from 0 to 440 degrees centigrade at sea level pressure. According to the ITS-90 standard, a simpler equation may be useful, and here's the equation. The density of pure liquid water is within 0.5% of 1,000 kilogram per meter cube over all typical conditions on the Earth continent, and is about 8% greater than the density of ice, but 2.5% less than the density of seawater. However, the small variation in liquid water density that occur with changes in temperature, pressure, and sometimes salinity are critical in aquatic dynamics. This is because even these small changes in density can lead to stratification of the water column, and in turn, motions within a stratified water column are strongly restricted to lie in the horizontal. At atmospheric pressure, the density of pure water increases from 999.843 kilogram per meter cube at the freezing point to a maximum of 999.975 kilogram per meter cube at 3.98 degrees centigrade, and then decreases at higher temperatures. Water is also nearly but not quite incompressible. For every meter of depth increase, the ambient pressure in a water column increases by about 1 decibар from its sea level value of approximately 10 decibar. As this water column pressure increase reaches 100 decibar, typically near a depth of 100 meters, density increase by about 0.5 kilogram per meter cube. More subtly, the freezing point and temperature of maximum density also decreases to 0.07 degrees centigrade and 3.78 degrees C, respectively, at that pressure. Usually water is in contact with the atmosphere and hence contains dissolved air. Air-saturated water has a density that is about 0.005 kilogram per meter cube, less than that of pure water at 0 degree centigrade, but only 0.002 kilogram per meter cube less than at 25 degrees centigrade. The isotopic composition of water can also change its density. The pure water value given here are for an isotopic composition found for water in the ocean, for example, the Visma. But this tends to be a little different from the isotopic composition of water in rivers and lakes, which usually has fewer heavy isotopes. Heavy water containing deuterium, H2, atoms has a density of about 1,100 kilograms per meter cube, but the range of density variation in typical water due to changes in isotopic composition from different natural conditions is no more than about 0.008 kilogram per meter cube. In most situations, it is the density differences between different but adjacent water masses that are of interest, and so correction factors arising from the presence of gases or different isotope composition which do not change much with temperature or location within a drainage basin are usually ignored. More importantly, the effect of adding dissolved matter to pure water usually results in an increase in density. This increase is approximately but not completely linear with the salinity. The density increase for a given increase in the dissolved matter is less at higher salinities. However, the amount of increase may also depend on the particular substances added. The density of seawater increases by about 0.8 kilogram per meter cube, as concentration of sea salt increased by a mass fraction of 1 gram per kilogram. And this is also a reasonable estimate for the variation of density with mass fraction salinity in typical lakes in which anion content is dominated by carbonate. However, if the dominant dissolved ion is carbonate or sulfate, then the density change can be up to 50% larger for the same salinity change. In addition, the temperature of maximum density and the freezing point decrease with increasing salinity. For seawater with salinity of 35 grams per kilogram, densities are greatest at the freezing point of minus 1.91 degrees C. So we can see this actually in this figure. So this figure maps the temperature and the x-axis and the density for different types of water. So one is a pure water, one is pure water at a pressure of 1000 decibar, and one is saline water with salinity at 35 grams per kilogram. So you can see that as these different waters are considered, the freezing point decreases slightly. And what we can see also is that the density also decreases as the temperature increase below the freezing point. And it's the same as the density decreases as the temperature increases above the freezing point. And as we all know, that we just went over, is that we have the highest density of water at about 3.98 degrees centigrade, which is what here more precisely. Finally, due to the nonlinearity of the equation of state, the density of a mixture of waters with different initial temperatures and salinities is greater than the average of the initial density. There is a slight contraction with mixing, most pronounced in colder waters, which can lead to downward convection or cabelling in areas where different water masses of the same density come together. Also, as the compressibility of water also depends on temperature and salinity, two water masses with the same density at one depth may have different density at another depth, the thermobaric effect. However, although the thermobaric effect has important consequences in the ocean, it is usually insignificant in its effect in lakes. Potential temperature and potential density. Not only is water slightly compressible, but its temperature will also change slightly as pressure is increased isentropically, i.e. without a loss or addition of heat, energy, or mass. The same phenomenon is responsible for the cooling temperatures with increasing altitude in the atmosphere, with drops of 4 to 10 degrees centigrade per 1,000 meters of altitude change, described by the adiabatic lapse rate as pressure drops with altitude. The effect is much smaller in water, however, with changes of only a few hundredths of a degree in temperature for a pressure change of 1000 decibars. Another difference with the behavior of air is that whereas above the temperature of maximum density, the temperature in water increases with pressure as it does in air, below this point, the temperature in water decreases with pressure. A common practice when the above changes are significant is to use a derived quantity called the potential temperature, often denoted by the symbol theta, in order to decide whether one fluid mass has more heat energy than another. The potential water of a fluid parcel is the temperature that would occur if the fluid was brought to a standard pressure, usually atmospheric pressure at sea level, isentropically, and thus it removes pressure dependence. Potential density is the fluid density at standard pressure with the temperature given by the potential temperature. It similarly accounts for pressure-related changes when deciding if one water mass is denser than another. Potential temperature and potential density are widely used in studies of the ocean and atmosphere and may be useful in studies of deep lakes where temperatures lie in a narrow range. For water, they are best calculated using TEOS-10 software.